We've got a good one today, folks. I have ESD on the brain because at work, somebody designed a circuit without any circuit protection. And it lasted about a year. Now I've got to fix it. So I came across this video. Microtype engineering, designing ESD safe circuits. And I said, ooh, simulation. Oh la la. I am interested. So, and then I saw, based off a website. Okay, I got this. I can make this. It took a lot longer than it looked, but I got it. So when I looked at that website, like, oh, IEC 61000-4-2. Yeah! Whatever that is. It's for ESD. It's like there's a waveform. Here's some specs. I love specs. I'm like, And he's pretty much got the same thing there. I like this. So I figure let's do this. Let's see what we can get out of this. So there's 4 different parts to the standard. Levels 1, 2, 3, and 4. And there's like a 5th one, which is kind of like whatever. So 2, 4, 6, 8 kilovolts. However, I have seen some data sheets on TVS diodes especially that go up to 30. So what the spec does not say is what you should use and when. So go high or go home, baby. So let's take a look. Let's go back up to our reference waveform here. And I just want to show you. Let me make this go a little bit smaller now. At the bottom of the screen. Okay, now what we do is current. Huzzah! Look at that. So, but it's a little stretched out. So let's go back here. If we do something like that, well, that is pretty much spot on from the picture. Let me get this back out because you demand evidence that this is correct. And I will give you evidence. So we're at 8 kV because YOLO, you only live once. First peak, 30 amps. Looks pretty close to 30 to me. Rise time, 0.8 nanoseconds. It's probably about right. About right there. We're not 10%, whatever, but that's close to 800. Done. What else do you have? 30. Then current at 30 nanoseconds is 16, 60 is 8. So let's go to 30. 16.69. There's like a plus minus 30%. So yeah, we're in there. 60 was 8. Come on. Was 8. So yeah. We're done good, baby. So. Alright. Now we know we've got an ESD gun simulated. Now it's time to play. So we've got our ESD here. I just put another net here because I could. Our 2 ohms is for the reference waveform. I'm going to go ahead and change that to like 0.1. When I was playing around, I found that I needed something there. Sometimes this particular simulation can get a little weird. So we'll see if it does that or not. Okay. So what's going on here? Let's get this big again. That way we can show you. this diode here, and this 1 meg simulate the input of an I/O pin on a microcontroller. They will all have this. So the good news is, this is why unprotected circuits may last a little bit longer than you would think. So let's just get into this right away. So what I'm going to be measuring is right here before the microcontroller pin. And what we'll see here is 5 volts, you son of a biscuit. Aha! 440 volts at the peak! Jeez Louise. Oh, this here, our voltage source, so this would just be VCC. I put a series resistance of 15 ohms. And that other guy's video was just like, oh, whatever. I'm like, no, let's not whatever. Let's see if we can get that dialed in. So the reason I chose 15 is because there's going to be caps here. There's going to be bypass caps, bulk caps. So their ESR at the 100 to 500 megahertz range, you'll be in this range of about 15. So that's why I chose that. Because we're not doing resistance at DC, like this is impedance. ESD is around 100 to 500 megahertz. So that's why we did that. Okay. So, unprotected circuit, 440 volts. So, and if you look at the current, 27 amps. Woo! That is how you break your shit. Okay, now let's look at some techniques we can use to get that down. Okay, so what happens if we just increase this? Let's just go to 22. See what happens. Right now we're at 440. And that, let's get rid of that current. And it went down a little bit. What happens if I go to, I don't know, 500? I mean, 180. Yeah, sure. That works. For ESD, that won't work for a whole bunch of circuits. If it's fast, forget about that. That's not happening. If it's I mean, that's current limit. So no, and look at that. You're still got a huge voltage. So no, this is bad. Like at best. It might, what are you doing? I only want 1 cursor, not 2. Get over here. So 407 versus 438. Just if you go with the 22 ohm, which 22 termination resistors are often 22. So that seems to, it might take the edge off, but it ain't going to solve the problem. No way. Now, what we'll look at next is, once upon a time, I saw a white paper. I digged it up and it was this one. Electrostatic discharge analysis of multi-layer ceramic capacitors. Basically, can you use capacitors for ESD? Yes. But if you don't do it right, you're going to break stuff. So I'll give you the summary. 0805, 10 to 100 nanofarad, 100 volt. And you'll be able to take a 25 kV transient. Whew! So, and I use it. Sometimes I don't want to spec a TVS diode, but I already have a bunch of whole 0.01 ohm resistors. Ohm? Microfarad. I go crazy sometimes. So let's go take a look. So I was just playing. Let's just do 0.1. We'll do an ideal capacitor. If we do that, wow! I need to expand my time there. Wow! Let's go to 500 nano. Okay. Then let's go to 5 microseconds. Woo! Well, I see why it works. That is a whole lot lower than 400. So the question you might be asking, so I'm at 5 volts here. Usually the absolute maximum is somewhere around 5.5 volts. So is this okay? The answer is yes. For very short periods. Like this will be fine. So we get to, do we get to 5.5? Just a little bit longer than this. We'd be at that 5.5 volts. So 5 microseconds, that ain't nothing. These are designed as protection diodes. You look at a data sheet, they'll call them either ESD diodes or protection diodes. So that kind of infers, that either infers that they're normal diodes and they're just giving them a special name, or they did something to make them beefier than what they would normally do in an IC. I don't know. But point being, we got that 400 volts down to something manageable. You can't have more than the absolute maximum for this very short duration. It won't hurt it. Just remember, we're trying to divert as much of that energy as possible. So if this has to take on a little bit, yeah, that's what it's there for. It's what it's designed for. So I also want to take a look at the current just to show you. I mean, 700 milliamps for just a few microseconds, that's fine. And we know this is fine. I've used this in a whole bunch of circuits. 0.1, it's fine. I didn't do the 100 volt. No way, everybody uses 50. But that's okay. Now, another thing I want to show you is I want to take this current off. What happens if you have a capacitor on there? So this would be like a bypass cap, 0.1. Right now, let's get this back up there. That way we can see our max. 16.83. So do that. Oh, snap! 11.4. That's what I'm talking about. But what if we did, say we have a big bulk gap in there. What does that do? Oh, whoa! Now we're talking. Even better. Wow. I'm almost speechless. But it makes sense, right? Your VCC is 5 volts, but this voltage from your ESD is higher. So that goes into your capacitors here, which makes it so your VCC does not rise as much. So yeah, use caps. You're using good decoupling capacitor strategies anyways, right? Close to the IC, big values, right? Right? You better be. Alright, just to pique my curiosity, let's do this 100 microfarad, but let's go to, all right, 25 volt. Let's see if using an actual model does anything. Right now we're at about 6.8. 8.7. Makes sense. We've got inductance, resistance. So yeah, makes sense to me how it went. So we are no longer in the ideal world. We're in the real world with part serial number. Good lord, man. Make your part numbers better, people. Wow, that is cool. Serial number. Okay, so now we know use decoupling caps, use bolt caps. Let's take those off. Get back to where we were. And let's do a little bit more experimenting. What if we did a 4.7? So, holy crap! Woo! That's only a little bit above the 5.5 max voltage rating of a 5 volt IC, typically what you see. Wow! Incredible! Small problem. You've slowed your circuit down so much that whatever you're doing may not be usable. So, that's cool if you can do it, but if you can't, then we need something else. The TVS diode! Okay, not really. If you look here, there's not much in the way of TVS diodes in this bloody program. So I picked the Zener 5.1. So we do that and click OK. Then let her rip. Oh man! That was pretty fast. You know what? I even wonder if the simulation is as fast as a TVS diode would be. It might be. You never know. So, but this is so fast, we've got to zoom in. So our max here is 10.5 volts. That's about what you'd see for the clamping voltage on a real 5 volt TVS diode. And if you look, we get to that 5.5 volts at about 120 nanoseconds. So this is very fast. So, yeah, buddy, they work. So let's see if I can break this simulation now. I think I broke it last time I tried this. What happens if I have my TVS diode far away from the connector? Or whatever is going into this. TVS diode is far away from the input. So we do that. Well, what do you know? Actually about the same. Well, it is actually a little bit higher. I think. I don't know. Right now we're about 10.2. Also, if you notice, my simulation is still going. Once you add inductors here, good lord, it takes forever. That's why I've been doing ideal, and when I haven't been, I've been praying that it'll work. What you gotta do is just close out of that, go back in, and then let her rip. So now let's look if we do more than one of these things at the same time. Let's get you back in there. And we're going to do 0.1. Although, let's actually pick a 0.1 that, good lord. Oh, I forgot to click that. do a 0.1. Oh, what did I see? Do 50 volt. Not electrolytic, you crazy people. Let's do that. See if it breaks. Now let's see what happens. Wow. That took the edge off. 7.5 volts for our peak. We're 5.5 here. 150 nanoseconds. Nice. Okay, now what we want to do, let's bring back our bulk caps. Or bulk and decoupling cap. Let's run that. 6.8. Oh, and now it's going forever because I have the inductance in here. Boo! So yeah, when I was running through this by myself, I was having this weirdo stuff happen, or sometimes where it would just break. So what we must also be aware of when we look at this is what is not present. One thing that's not present is some of our parasitics. Just because this happens and it breaks it. Parasitics of the traces. Board stack up. If you're using a good stack up, you'll have a good capacitance. You may have power plane, ground plane, maybe capacitance. Or if you don't have a power plane, you'll have a ground plane that's close to your signals. That helps. That is not in here. Also, good and bad layout practices. We didn't look at what happens if this is further away. That goes for them both. I mean, this right here, this 50 milliohm, kind of simulates trace impedance. But does it really? Because we're at 100 and 500 megahertz. No. Yep. I've got ESD on the brain. Still do, even after all this. I was just ended up reading some stuff. I was like, what is true? What is not true? I've actually seen this technique used in a circuit, except they did a 330 picofarad. I'm like, where'd this value come from? Does it actually work? Does it do anything? Well, the answer is, I guess it does, just not really. Close out of this and reopen it. Oh, I think we were at 12 before, so it's like barely nothing. Barely nothing. Barely something. All right, one thing I didn't really show you. Current! Oh, and let's take that out. That didn't really change. Current, the waveform looks mostly similar. I saw one thing online that said, for these brief moments, it is okay for these to take full-blown amps because this is so short. So I really tried finding something that could talk about these a little bit more other than they exist. But just couldn't do it. So this also brings to light something you see when you look at 5-volt TVS diodes. That is that their clamping voltage is typically around 9. Maybe 10, 11 if you're having a bad day. So I wish these data sheets would go into that a little bit more. And for the 3.3 volt as well, for their clamping voltages. None of them said it's okay. So I looked at the clamping voltage and I said, it's higher than the max. So after exhaustive research, it's okay. Those TVS diodes can go above. You are above the limit for such a short period of time and you have these ESD diodes to protect you, you are okay. So go for it. So just to recap, resistor only, not really. It'll take the edge off, at best. But there would be a whole bunch of voltage here. So what I would do for something like this, just to play it on the safe side, 0805, the voltage rating there might be only 50 volts. But I know if you go up to 2512, that'll be closer to 500. It would take this, no problem, especially since it's such a short duration. Now, as for this, typically what I do is go big or go home, as far as package size. Another thing we are not mentioning is don't have this go to signal ground. For simulation purposes, it doesn't matter. In the real world, your TVS diodes should be connected to chassis ground. And if you don't have a chassis ground, you should get one. Or make one. Because this ESD voltage, this is the simulation here at 8 kV. This is a simulation if somebody were to directly touch a pin on your product. So this is a direct contact. You can go up to, they do have a standard for just an air discharge. So the equivalent of this 8 kV would actually be 15 kV. But for simulation, do direct contact. And in the real world, do direct if you can. Air discharge, I hear, has some variability associated with that. So yeah, just touch the pin, make it 8K or 30K, whatever you need. That might be something interesting we can do right now. Change this to 30. Then, holy crap! So much! So remember, I was measuring right here. We go right there. 24 volt, that's still a lot. So that is why you do all the other stuff here. Defense in layers will make your circuit very happy. Now let's do that. 11.2 from a 30 kV blast. Then we go back down to our 5.5. Hey, I'm watching you. Oh, it's not done yet. See, weird things happen. But if you select what's already done, then you can do that. So 5.5 volts. I think we were at 150 nanoseconds last time. Now we're at 220. Yeah. So ESD protection. Very important. If you don't do it, I will find you and make you do it. Don't forget this stuff. I've had to redo people's circuits because they forget this stuff. Don't be that person. So I hope you found this a little entertaining, mostly informative. I hope you learned something new, and I hope you will protect your circuits from now on. This is Steven, over and out.